In this video, we want to continue where we left off in the last video and look at a similar problem, still seeing if a given element of a vector space is a linear combination of some other vectors in that vector space. But this time we'll look at vectors in the vector space M22, which, if we remember from our last lecture, is the vector space of all 2x2 real matrices. And so let's take a look at this thing and see if we can complete this the same way we handled the last one. Might look a little different because we have matrices rather than just row vectors, but the process is still exactly the same. We want to see if this 7, 6, -5, -3 matrix, that's like our V here, can be written as a linear combination of these three matrices. We set it up exactly the same way as before. We say the given matrix 7, 6, -5, -3 equals a scalar times one of the matrices plus a scalar times the other plus a scalar times the third. So writing this down, it's going to look like we need to solve or try to solve this matrix equation. That's the matrix we're starting with. We ask, does it equal a linear combination of these other given matrices? Well, if this guy we started with can be expressed as a linear combination of these three, that would mean that there's a solution, C1, C2, C3, to this equation that we can find. So we try to find it. And again, all we're going to do is say we have a matrix on the left, we have a sum of matrices on the right, which is still just a matrix. So in order to figure out what scalar equations this unpacks into, we're just going to equate the corresponding components on the left equal to the sum of the corresponding components on the right. So for example, we would know that this matrix equation is telling us 7, the entry in the first row, first column of the left matrix, must equal 3C1, 0C2, I'll even write it here so it's clear, plus 1 times C3. That's just from multiplying these scalars into the matrices and seeing what those first row, first column components look like. Well, we'll do this for every component. First row, first column, second row, first column, first row, second column, second row, second column. Let's write that system that we get down. Let's see. Looking at second row, first column, it looks like I also get -5 equals 1C1 plus 3C2 plus 0C3. Looking at first row, second column, we get 6 equals 0C1 plus 1C2 plus 2C3. Finally, last row, last column, -3 equals 1C1 plus 4C2 plus 1C3. And wouldn't you know it, again, this idea of determining whether one vector is a linear combination of others amounts to just solving a linear system for those scalars C1, C2, and C3. I'll do this the same way I handled it before. I'll unpack this system, or I guess pack it up into an augmented matrix. Let me do that real quick. And that's the augmented matrix we get. And again, we just want to solve this by reducing this down to a point where we think we could easily unpack it and solve the system. When I do that, again, I'll save you the trouble of showing all those row ops, but I do just get here by row ops. I get the reduced form of this matrix looks like 1, 0, 0, 1, 0, 1, 0, negative 2, 0, 0, 1, 4, and I get a row of zeros at the bottom. That's what I end up with. And again, this is trivial to unpack. Notice that last row there, that row of zeros, it's just telling us 0 equals 0. Nothing useful, but nothing contradictory either. So all we're focusing on is those first 3 rows, which we can unpack into the solution C1 equals 1, C2 equals negative 2, and C3 equals 4. So we were able to solve the system. This means we can write our original matrix Sorry about that. Myself a little more room there. We can write that original matrix as C1 times the first matrix minus 2, which is our C2 value, times the second matrix plus 4, our C3 value, times that last matrix. Here we have the original written as a linear combination of those 3 matrices, which are really vectors if we consider them in this vector space M22. Okay. So we'll do another example that gets even a little bit stranger, a little less like Rn even than this is, in the next video.